Okay, so in part 4, we are to determine the invariant factor decomposition of the group G. And this one we can almost do by inspection. Notice that the direct product of the integers modulo 4 with the integers modulo 15 is isomorphic to the integers modulo 60, since the greatest common divisor of 4 and 15 is 1. And so the group G is isomorphic to the direct product of the integers modulo 60 with the integers modulo 12. Further, 12 does divide 60, since 60 is equal to 12 times 5. And so we have that the group G is isomorphic to the integers superscript 0 times the integers modulo 60 times the integers modulo 12. And this is the invariant factor decomposition of the group. And by the fundamental theorem of finitely generated abelian groups, this factorization is unique. That is, there is no other way to factor the group G such that the order of each finite cyclic group divides the order of the finite cyclic group that precedes it. Now, in this lecture, we'll look at an algorithm for determining the invariant factors of a finitely generated abelian group. So in part 5, we are to determine, is the group G decomposable? Now we know that the group is isomorphic to the product of two groups, the direct product of the integers modulo 60 with the integers modulo 12. Now the integers modulo 60 is isomorphic to the product of the integers modulo 4 with the integers modulo 15, which itself is isomorphic to the product of the integers modulo 4 with the trivial group with the integers modulo 15, where this product, the product of the integers modulo 4 with the trivial group with the integers modulo 15, is a non-trivial proper subgroup of the group G. Further, the integers modulo 12 is isomorphic to the product of the trivial group with the integers modulo 12 times the trivial group, where this product, the product of the trivial group with the integers modulo 12 times the trivial group, is itself a non-trivial proper subgroup of the group G. And so the group is isomorphic to the product of two non-trivial proper subgroups, and hence the group G is decomposable. So new definition: an integer n is square free if and only if it is not divisible by the square of any prime and so a square-free integer is either a prime or is the product of distinct primes. So as a corollary of the fundamental theorem for finitely generated abelian groups, if the integer n is a square-free integer, then up to isomorphism, the only abelian group of order n is the group of integers modulo n. So proof: let G be an abelian group of order n, where the integer n is a square-free integer, then by the fundamental theorem for finitely generated abelian groups, the group G is isomorphic to the direct product of the integers superscript 0 times the integers modulo n sub 1 times the integers modulo n sub 2 and so on through the integers modulo n sub s, where each invariant factor n sub I is greater than or equal to 2, and n sub I plus 1 divides n sub I for I greater than or equal to 1 and less than or equal to s minus 1. So if P is any prime divisor of the integer n, then P divides n sub I for some index I in the range from 1 to s, since n is the product of its invariant factors, n sub 1 times n sub 2 and so on through n sub s. But then the prime P divides n sub j for all j less than or equal to I. And so P divides the first invariant factor, n sub 1, that is, any prime divisor of n divides the first invariant factor, n sub 1. Now, since the integer n is a square-free integer, and hence is either a prime or the product of distinct primes, we have that n divides n sub 1, the first invariant factor, and hence n is equal to its first invariant factor and its only invariant factor. And thus the group G is isomorphic to the direct product of the integers superscript 0 times the integers modulo n. And therefore the group G is isomorphic to the integers modulo n. So for a square-free integer n up to isomorphism, there is only one abelian group of that order, and that is the group of integers modulo n. So let's look at an example. 6, which is 2 times 3, is a square-free integer. So every abelian group of order 6 is isomorphic to the integers modulo 6. Now let P be a prime and let alpha be a positive integer. The number of abelian groups of order p to the power of alpha up to isomorphism depends only on the number of possible partitions of the power of the prime, alpha, and is independent of the particular prime, P. So let's look at an example to clarify that. For example, 8 is the prime 2 to the power of 3. The possible partitions of the power 3 are 3, 2 and 1, and 1, 1 and 1. And so there are 3 abelian groups of order 8 up to isomorphism. We have the integers modulo 2 to the power of 3, which is the integers modulo 8. We have the product of the integers modulo 2 to the power of 2 times the integers modulo 2, which is the integers modulo 4 times the integers modulo 2. And we have the product of the integers modulo 2 to the power of 1 times the integers modulo 2 to the power of 1 times the integers modulo 2 to the power of 1, which is the product of the integers modulo 2 with itself 3 times. But notice that these 3 possible abelian groups up to isomorphism are determined by the possible partitions of the power of the prime, which is 3. So we have the prime to the power of 3, then we have the partition, the prime to the power of 2, and the prime to the power of 1. And finally, the partition, the prime to the power of 1, the prime to the power of 1, and the prime to the power of 1. So recall that if n equal to p sub 1 to the power of a sub 1 times p sub 2 to the power of a sub 2 and so on through p sub r to the power of a sub r is the factorization of n into powers of distinct primes then the integers modulo n is isomorphic to the product of the integers modulo p sub 1 to the power of a sub 1 times the integers modulo p sub 2 to the power of a sub 2 and so on through the integers modulo p sub r to the power of a sub r. And we can use this fact for every factor in a group. So let's look at an example. Again, let the group G be the direct product of the integers modulo 4 with the integers modulo 12 times the integers modulo 15. Since 4 is 2 squared, that is the power of one distinct prime, we cannot factor the group of integers modulo 4 any further in terms of powers of distinct primes. And since 12 is 2 squared times 3, the integers modulo 12 is isomorphic to the product of the integers modulo 4 with the integers modulo 3. And since 15 is 3 times 5, the integers modulo 15 is isomorphic to the product of the integers modulo 3 with the integers modulo 5. And so the group G is isomorphic to the product of the integers modulo 4 times the integers modulo 4 times the integers modulo 3 times the integers modulo 3 times the integers modulo 5. Now, in general, if the group G is isomorphic to the product of the integers modulo p sub 1 to the power of alpha 1 times the integers modulo p sub 2 to the power of alpha 2 and so on through the integers modulo p sub r to the power of alpha r, where each p sub I is a not necessarily distinct prime, and each alpha sub I is a positive integer, then the integers p sub I to the power of alpha sub I are called the elementary divisors, of the group G, and this factorization of the group G is called the elementary divisor decomposition of the group G.